All right, welcome to what might be. Now, earlier I had said that this was the most important thing when it was multigram convergence. All right, I'm going to go out on a limb here, not much of a limb here though, and say the most second important video of the entire course. It's going to be on stoichiometry, and I'll explain what that means and how to do it in this video. Importante, grande video nado. Now, I left this last problem up here on the board because I realized once I had shut the video off, because it was over 22 minutes, and then I said, I turned around to erase it, and I just went, oh crap, maybe some of you might have this question. Because remember earlier, and that was the third problem down that I had set up, you had a 2 and a 3, right? And I said, well, multiply them together. Try to get 6 on both sides. And so some of you might be saying, well, why didn't we do the same thing here? We had 2 here, and we have 4 and 3 and 7 here. So that's 2 and 7. Why not just multiply together and get 14? The reason you can't do that method here, that strategy, is because the 2 and the 3 were, whatever, I don't remember what those elements were anymore, but we had 2 of them and 3 of them. Maybe it was nitrates. I don't remember. But the point is, those 2 and those 3 were wrapped up into one compound on the left and one compound on the right. Here, the compounds are split. The compound here is split where the oxygen has 4 here and 3 here. That method will not work if you have a split element that you're trying to solve for with that particular method. That's why I had to go through and put 3.5 here to balance it, and then double everything. So if the elements that you're trying to balance are split into 2 or more compounds, you can't take how many on the left and how many on the right and multiply them and get that many. So it would not work. That method would not work. That strategy would not work with this compound because the oxygens are split into 2 compounds. Okay, now I'm going to go back to my water. Now this is nice and balanced, okay? We have to balance chemical reactions for the reason of don't violate the law of conservation of matter. Don't be a law violator. Second reason is you got to have a balanced reaction to do stoichiometry. That is a scary sounding word. Scary. German word. Stoichiometry. All right, now what that means is taking a balanced reaction and using a balanced reaction to solve for mass, usually solve for mass amounts. How much you're going to be able to calculate, how much you're going to be able to get, how many moles or how many grams of product are you going to get from a balanced reaction. Usually. It doesn't have to be. And stoichiometry can also be used to find how much reactant will react. If I know how much product was made, then I can go ahead and figure out how much reactant must have been used. So stoichiometry is using a balanced chemical reaction to calculate masses or moles from a balanced reaction, and either can be products or reactants. So you're calculating the amount of mass or the amount of moles of something in the balanced chemical reaction, usually products. All right, so here is a balanced reaction, and the first thing I want to talk about was called the mole ratio. The moletile is an Italian word, yes. All right, the mole ratio is shown here by the coefficients. So we look at the coefficients to know what the mole ratio is. This mole ratio is 2 to 1 to 2. 2, 1, 2. Okay, now, let me give you an example of how we can use the mole ratio in predicting product or predicting reactant, depending on which one we're trying to find. Chocolate chip cookies. Chocolate chip, yes. How does that have to do with chocolate chip cookies? Okay, stick with me, please. If you want to make chocolate chip cookies, now I've actually personally never made chocolate chip cookies. I know, it's on my to-do list. But I know that you're going to need, well, chocolate chips. You're going to need flour. You're going to need sugar. I think you're going to need milk and eggs and butter. I don't know. But let's just say that I know I need those ingredients. Maybe some vanilla, whatever you throw in your chocolate chip cookies. But I don't know the amounts. So here's what I'm going to do. I'm going to take a shot at it. I'll make my first batch of chocolate chip cookies. I'm going to get a mixing bowl. I'm just going to pour in like half a gallon of milk. I'll take a bag of flour, dump that in, a couple bags of chocolate chips. I'll take 4 sticks of butter. Okay, I'm all buttery. What else do I need? Sugar, a cup of sugar. Throw that in there. And then go ahead, mix it all up and put that on a pan and put it in the oven. Gonna be good, right? Gonna taste good, right? You wouldn't want my chocolate chips, right? Probably not, right? Because I don't know the ratios, the amounts of each ingredient to make the amount of product that I'm gonna need. That means ingredients, being milk, sugar, to make my chocolate chip cookie product. Okay, I don't know what I should be using and what relationship of how much I should be using to make that chocolate chip cookie. That's what a balanced chemical reaction is. It's the same thing. This is chocolate chip cookies. Chocolate chip cookies, okay? Mind powers. Here are my ingredients. I need a little hydrogen, I need a little oxygen because I want to make some water. Okay, I want to make good old high quality made in America water. So I go to my chemical cabinet, open it up, look for, it's alphabetical order, so look for, there it is, H, hydrogen. I find my jar of hydrogen, set that down, let's get the oxygen, oh, oxygen, got those, set that down, pick these up, got my 2 jars of hydrogen and oxygen, okay, and I have my cauldron, maybe it's a witch's cauldron, yes, witch's cauldron, and I take the top off the hydrogen, I dump that in, okay, get that hydrogen in there, okay, do the same thing with the oxygen, take that, dump that in, mix it up, and I'm gonna get water. Several problems with that, okay, see if you can figure all of them out, what's wrong with that picture. Point is, you can't just throw the stuff together and expect to get this. You got to do it in the right amounts. What I'm going to need 2 hydrogens for every oxygen to get my water. 2 hydrogens with 1 oxygen will give me 2 waters. Now, let's go back to chocolate chip cookies. Let's say you want to make a double batch. You got a bunch of people coming over, you want to make double batch of chocolate chip cookies. What do? You know what you do. You double all the ingredients. You double everything to make double the product. Let's say I don't want to make 2 waters. Not enough. I want 4 waters. What am I going to do? Double the ingredients. This tells me how much of the ingredients I need, my coefficients. So I'm going to double. I'm going to go and get me 4 hydrogens and 2 oxygens. And that'll make me 4 waters. I've doubled everything and I've got double product. We just did stoichiometry. Yes, we did. We just did stoichiometry. We used a balanced chemical reaction showing the ratios of how much of the stuff I need. And we're going to be talking about these coefficients mean moles. Okay, not just like molecules. We're talking moles here. We're going to be dealing with moles. 2 moles of hydrogen, 1 mole of oxygen make 2 moles of water. And we did a problem where I said, well, what if I doubled the 2 reactants? What would I get? You know what the answer to that is. You can see that. This is a stoichiometry problem because I just used balanced tiles, balanced ratios, and predicted product. All right? So once you predict that product, you have done stoichiometry. Now, typically, we are not going to be able to just look at them and predict. Okay, they're not this easy. I know. Well, you know, we got to make things a little more challenging. No, you don't. Yes, we do. So this is an easy stoichiometry problem that we can see what's going to happen for the result. We are not going to be able to see very many problems. We're going to calculate them, and we have a method for that, and we will get into that shortly. But let's do another one where you could probably see the answer before we do it out. All right, so let's use my water reaction. And let's say that what I want is 32 moles of water. What am I going to have to use to get 32? All right, well, 32 is 16 times greater than 2 than my original recipe. This is my recipe to make water. So I'm going to need 16 times the oxygen, 16 times 1, and I'll need 16 times the hydrogen. 16 times 2 is 32. Look, it's the same proportion, it's the same ratio. And we just did stoichiometry. Yes, we did. All right? Okay. So that is how we do stoichiometry. Now, you're not going to be able to just look at things and predict them very easily. Let me give you an example of that. Let's say that I wanted to make 550 grams of water. All right? How many grams of hydrogen and how many grams of oxygen am I going to need? A little different, isn't it? Yeah. Or the opposite could be true. What if I had 300 grams of hydrogen and 500 grams of oxygen? How much water in grams or moles could I make? That's a whole different ball game. Okay, harder, can't do that in our head. In fact, this one would actually be called what we call the limiting reactant one, which is a further down the line. We won't do that. But this is a stoichiometry problem. We're predicting product, and this time we have grams. Oh, how are we going to get that from the balanced reaction? Okay, all right, hang on. Okay, now here's what I have done for you. I have copied in to Essential Documents Stoichiometry practice problems. Yes, we're going to practice with these, hence practice problems. So you go get that, and let's do some stoichiometry. Now we're going to go from off the stove to jumping in the frying pan on this, because this is going to involve a lot of chemistry. Actually, you know what? Before we do that, I don't want you to jump into the frying pan. You didn't have your frying pan protective gear on, so let me go back and put the water back up here. And we'll do one with the water. A little harder, but we'll do one with the water. All right, balanced chemical reaction. And I also want to talk about the mole ratio. That's going to be really important. Not the mole ratio that's shown up here, but a different mole ratio. That's really important, this mole ratio. So let's go ahead and do this. Okay, here's a question. All right. Given 3 moles of hydrogen, if I asked you how many moles of water could we make, I hope you can see the answer to that right now. I hope you can. That's not going to be my question, but I hope you can. Because 2 of these makes 2 of those. 2 of these will make 2 of those. So therefore, 3 of these should make 3 of those. I should be able to make 3 waters, so 3 moles of water. Okay? That would be what is called a mole-to-mole stoichiometry problem. There are 3 kinds of stoichiometry problems. 3 kinds. Put them right here. 3 kinds. 1, mole to mole. And that's the easiest kind to do. If you know the balanced reaction and you know how many moles of one thing you have, you should be able to predict how many moles of the other thing you're going to need. All right? So 3 of these should make 3 of those. 8 of these should make 8 of those. Okay, that's a 1-to-1 relationship. Okay, here, how about this one? How about 8 oxygens? If you had 8 oxygens, how many could you make? How many waters could you make? That's a 1-to-2 ratio, 1-to-2. So if I had 8 of these, 1-to-2 is 8 to 16. I should be able to make 16 because it's twice as much water that I can make from the oxygen, so twice as much. I hope you can see those. Those are mole-to-mole conversions. They're the easiest ones, and sometimes you can see those. If the numbers are kind of funky and weird, sometimes you have to write them out, but usually you can see those. Mole-to-mole, and that's also what's called a one-step. This is a one-step problem to solve. Second kind is going to be moles to grams. I put a double arrow, meaning it could be that way too. You go grams to moles. Moles to grams or grams to moles. That is a 2-step problem. A little more involved. And third is a gram to gram. I have arrows going both ways because it could be grams of product, how many grams of reactant would you have to use, or it could be how many grams of reactants I have, how many grams of product I could make. So a gram to gram, you got it. Come on, you know the pattern. 3 steps. This is a 3-step conversion. All right. No matter which of these we're going to use, the 1-step, the 2-step, or the 3-step calculation, the 3-step stoichiometry problem, we are always going to use what's called a mole ratio. Now, I'm going to put here, with the star next to it, nope, 2 stars, no, 3 stars, no, 4 stars. 4 stars, that's pretty good. If you're a 4-star general, that's pretty good. All right. So that means that's important. Mole ratio. Oh, I put the word mole, a ratio. Mole ratio. Mole ratio is always used in any stoichiometry problem. A mole ratio will always be used. Always, always. Aren't too many alwayses in chemistry. Here's one of them. Mole ratio is always used, and I'll put ST for short, stoichiometry problems, once. One time. You'll always have a mole ratio that will appear in your calculations once. Now you're saying, what's a mole ratio? Are you talking about the 2 to 1 to 2, the thing that's up here, the ratio of the, kind of, but not really. Here's what it is. The mole ratio is where you're going to have in your calculations moles on top and moles on the bottom. If you have moles over moles, you have what's called a mole ratio. I mean, that should make sense, right? Because mole ratio, moles over moles is a ratio. When you have that, you have a mole ratio. Let me show you what I mean by solving this problem for this. Let's say that I have, well, let's go ahead and go back and do this. Let's go 10 waters should equal 10 hydrogen should equal how much water? Well, you should know that 10 should equal 10 because we can see it. We can see it in the math. But let's set this up. We have to do dimensional analysis. Oh, yes, we do. Remember, I told you dimensional analysis can be really important when it comes to stoichiometry. So we have to be able to use that, do that. If you don't know how to do it, you're still confused, then you got to get it. Stoichiometry is going to be a nightmare for you. Well, if you know how to get it, stoichiometry is not that bad. Okay. Sounds bad, but it's not that bad. So what I do in any conversion, dimensional analysis, write down what I know I have. That's what you always start out with. I have 10, and these numbers represent moles, 10 moles of hydrogen. Multiply, divide, because that's what you do when you do dimensional analysis. And whatever is here goes down here. Moles of H2. All right, now, rocket's red glare bursting in air. Every time that you are doing a stoichiometry calculation using a nice balanced reaction, trying to predict product, every time that you put moles of anything from that reaction on the bottom, you have a mole ratio. You have a mole ratio. So we got to write that down somewhere. That's important. Now I'm going to write it down here, and then later I'm going to erase it. So you've got to write this down. You got to know this. So the first time moles appears on bottom of that fraction, you have a mole ratio. And remember the thing about a mole ratio. Mole ratio is going to be moles and moles, top and bottom, and you only get one of them in every single problem. So the first time that a mole appears on the bottom, I have a mole ratio. Ding, 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 I have a mole ratio. What does that mean? That means moles is on the bottom, and I have to put moles of something on the top. I have to put moles of something on the top. Now, it's America. You can put whatever you want up there. I would stick with the equation. Don't go outside the equation. That would not work. So you can put moles of water. You can put moles of oxygen. Okay, you can put whatever you want. But let's solve the problem. The original question was, if I had 10 of these, how many of these could I form? How much water could I form? So I'm going to put moles of water up here because that's what I'm trying to find. Put what you're trying to find. Put moles of H2O up there. You're trying to find that. All right, so now I need numbers that go in here. I need numbers that go in here. You said a 1 always goes next to the mole. That is absolutely correct. If, remember I did warn you that the 1 going next to the mole might not always happen in the next week, which is now, if you're going from moles to grams. You're not going from moles to grams here. You're going from moles to moles. That's what a mole ratio is, moles to moles. Actually, I call the mole ratio a gear changer. It allows you to go from some substance to a new substance. It allows you to calculate from one thing to another. The gear changer. It's a game changer. That's a big thing that's thrown around now. Everybody says that now. Oh, it's a game changer. Okay. Where do I get the numbers? From your balanced chemical reaction. That's why you have to have a balanced chemical reaction, or you can't do stoichiometry. We balance the reaction. We know that the mole ratio is right here. 2 hydrogens, so I put 2 here from the balanced reaction. From the balanced reaction, I have 2 waters. Right there. Nice. That's it. Now, this is going to cancel out moles of the hydrogen and leave me with moles of the water. And is that not what I was trying to find? I was trying to find, if I have 10 moles of hydrogen, how many moles of water will I may be able to make? So this is going to find what I was looking for. It's a one-step conversion. Notice, mole to mole. We had moles of hydrogen. We're calculating moles of water. Mole to mole conversions, one step. So we have one step, and now we're going to get the answer. 2 divided by 2 is, cancels, so the answer is 10. Like we had predicted. We had predicted that 10 should make 10. We can see that, but I just wanted to show you mathematically how to do that one step, because most problems aren't one step. They're 2 and 3 steps. So we are going to have to start out relatively easy and then work our way up. So I didn't throw you into the frying pan like I was going to for the stoichiometry practice problems, but I will in the next video. Okay. With this one, just to wrap this video up, we do have a mole ratio, as we said. The mole ratio is only used one time, no matter what kind of a 1, 2, or 3 stepper you're using. So we did have one. And mole ratio appears the first time moles are on the bottom. So we did have that mole ratio to solve that problem. All right. Oh, no, long video. Okay. Cutting out.